Welcome back to our final video on what happens when we have intersecting lines and circles. And this time we are looking at our very last version, which is what happens when we have tangents that intersect. So we can see here we have two tangents, AP and PB, and they intersect outside the circle naturally because tangents don't go inside the circle, so they have to have their intersection outside the circle if they intersect at all. And again, I've highlighted here the arcs that we're looking at. We're looking at arc AB, that minor arc. Again, that's always going to be a minor arc, this near arc. Try to convince yourself why that has to be true. And major arc ACB here, and that's always going to be a major arc. And maybe you can convince yourself why that has to be the case too. And we can look at this angle here, angle P, and see what it equals. Let's see if I can make the numbers a little nicer here, maybe make that 120. And we can see a relationship here. And that relationship appears to be the same as the exterior angle formula that we had before. When we had an angle that was formed by two secants or secant and tangent intersecting outside the circle, it's the far arc minus the near arc divided by 2. So 240 minus 120 is 120, divided by 2 is 60. I could do that with this angle being, let's see, 130, let's say. Let's keep the numbers easy. 230 minus 130 is 100, divided by 2 is 50. Good. So that still works just like it did before when the intersection was outside the circle. And if you want to do that proof, you're going to, again, you're going to bring in the assistance of an arc, AB here, and maybe you can figure out what angles A and B, what those two inscribed angles have to be, and then hey, what kind of triangle is this? What do you know about the tangent segments here? What kind of triangle have we formed? That's going to be very, very helpful for figuring out this angle here. You could also, by the way, do this problem by figuring out this angle out here, BA, and then down this way, the one that intercepts this big major arc. You could do that way as well. There's one other way of looking at this that's pretty interesting. And I'm going to draw in the radii here. By drawing in the radii, what kind of shape have I created? PAOB. Stop and think about that for a second. What kind of shape is this? And what kind of angles are formed at A and B? Once you have that, that is going to help us to figure out a relationship between angle P and the central angle AOB. And maybe there's a relationship here between those measures. And that's a special relationship that arc AB, which is the same as the central angle O, plus angle APB, that's always going to be 180. Let's go back to how this started out. Let's see, 120, does that still work? 120, 120 and 60? Yep, those add up to 180. So that is our special theorem, that this only works for intersecting tangents. That the sum of the angle formed by intersecting tangents is the intercepted minor arc, plus this angle is always 180 degrees. In other words, this angle is 180 minus the minor arc. That's a special formula only for intersecting tangents. If you don't want to remember an extra formula, don't blame you. The exterior intersection equation still works. We have two objects intersecting outside the circle that have a relationship to the circle, right? We still have intersection points on the circle, right? PA and PB, we have these intersections A and B. So that formula about intersecting outside the circle still applies, that it's 1/2 of the far arc minus the near arc. So that's it for this video. In the next video, I'm going to summarize all of these angle and circle measures all together so we have it all in one place. See you then.